Okay, question 3. Based on the given phase portrait, discuss the long-term behavior of the population of both species. So here, if we sketch the phase portrait for the problem above here, this will be the phase portrait. Um, here we can see the 4 equilibrium points. Okay, the equilibrium points we have, the first one is 0, 0. The second one is 0, 20 here. The third one is 25/20 here. The fourth one is I think somewhere here. Okay, 14, 2, right? Minus 2, sorry, the fourth one here. About 14 minus 2 here. Maybe here minus 2. Yes, this is minus 2.5. Okay, so somewhere around here. So if you find the solution, okay, previously in the previous question we find its eigenvalue. So actually if you try, you've already can determine the type and stability. There are many things actually we have from the eigenvalue. We know already the type of its analytical solution, right? Because we learned in the eigenvalue method, when we have the eigenvalue that all negative, we know the form of solution will becomes, we have two exponent of negative function in its analytical solution. If we have the complex eigenvalue, for example, we have the sine and cos function. Okay, we know, I hope that you can relate with the form of general solution with the phase portrait as well, right? The phase portrait for this, the complex without real part, actually we have a circle, or the name is center. Okay, if we have with the real part, then we have a spiral and so on. Okay, so in this case, different equilibrium point, different initial population will leads to the different type of solution actually. So if the two interesting one, I think, for this this point, I think, okay, 0, 20 and 25/2, 0. Okay, the second equilibrium point and the third equilibrium point. So equilibrium point 0, 20 is here. Okay, 0, 20 around here, and equilibrium point 3, this is for 25/2 is 12.50. Okay, so 12.5 somewhere around here. Okay, so it's actually, we see that the problem, the long-term solution that will leads to this point for the equilibrium point 2 will be if we have the initial population in this vicinity, right? And also in this vicinity. Okay, the solution that relates to this point, I think if we have the solution initial population around here. Okay, because if we have here, we see it will increase, approach this. Okay, so somewhere very small enough here will leads to this equilibrium point. Okay, so what does it means? I take the clear one here. Maybe let's say the initial population for like for the x and y is here. Okay, so there there is some value for x, means population for x is here about, let's say 7. Okay, initial population for species y here, let's say 26. Okay, so the arrows means t increasing. So we see, okay, as we have discussed before, we see the pattern here, y decreasing. Okay, we see the movement of the arrow here towards negative x, okay, and negative y, sorry, not negative y, lower y, right, towards the left hand side, and downward means y and x getting smaller. So it will getting smaller, and then after some point here we see this line represent y increase. Okay, but final x species continue to decrease, right? And finally it reached this point. This point is the point 020. Okay, this is the interesting case that I mentioned in the lecture outline, the survival of a single species. Okay, in which here which population survive is referring to this. This is x, this is y. So means in a long term, species x didn't survive. Okay, not survive, unable to survive. Only one species that managed to survive, which is the species y, right? Similar with the third equilibrium point here. This is also the case where only one species managed to survive. Okay, maybe if we have very small value for x here, okay, it will approach to this point. So only one managed to survive. If we have initial population around here, very small value for y. Okay, so y didn't survive, only one species, which is x, managed to survive. Its long-term solution is this one. For other points, the other point that we have is 0, 0. 0, 0 is unstable. Okay, it's actually still leads to this point, right?